Okay, in this class we define two definition, that is countable sets and uncountable sets. Countable sets and uncountable sets. Definition is like that. Suppose we have a set S, then we say that the set S is a countable set. The set S is a countable set if S can be written in this form, that is S can be written as set x1, x2, x3, etc. If S can be written in this form, that is x1, x2, x3, etc. in this form, at this time we can say that the set S is a countable set. For example, consider the set of all natural numbers n. Consider the set of all natural numbers n. We know that the set of all natural numbers is 1, 2, 3, 4, etc. We can write set of all natural number is like this: x1, x2, x3, etc. where x1 equal to 1, x2 equal to 2, x3 equal to 3. This is the set of all natural numbers. That is, we can be written as n as set x1, x2, x3, etc. where x1 equal to 1, x2 equal to 2, x3 equal to 3, etc. So we can say that set of all natural numbers is a countable set. Another example is that set of all integers. Set of all integers, we know that set of all integers is 0, 1, minus 1, 2, minus 2, 3, minus 3. We can be written this set as x1, where x1 equal to 0, x2 equal to 1, x3 equal to minus 1, x4 equal to 2, x5 equal to minus 2, x6 equal to minus 3, x7 equal to minus 3, etc. So, set of all integers set can be written as x1, x2, x3, x4, etc. So, set of all integers is also a countable set. Okay, we defined the definition of countable set. Next, we are going to define uncountable set. Uncountable set. The set S is cannot be written is in the form of x1, x2, x3, etc. If the set S cannot be written in the form of x1, x2, etc. is called uncountable set. In other words, if S is uncountable, when S is not countable. That is, if S cannot be written in this form, S cannot be written in this form, at that time we can say that the set S is an uncountable set. Okay, next we are going to define, write a theorem. Theorem says that if we have two set A and B, that is A subset of V. We have two set A and B and a subset of V. And the theorem says that the smaller set A is uncountable. That is, A contains huge number of elements. That is uncountable set. Then of course B is also a uncountable set. The set A is uncountable, which means that B is also uncountable. Okay, another is that if B is countable, that is B itself a small set, that is only a countable number of elements is in B, then the second part of the theorem says that if B is countable set, then A is also a countable set. It's a logic. We can use, we can understand this theorem by using our own logic. A subset of B. If A is uncountable, which means that A contains huge number of elements, then of course the higher set B is also uncountable set. The second part of the theorem says that if A subset of B is a countable set, that is only small number of elements is there, then the smaller set A is also a countable set. Okay, the proof is not important for us now. I am going to prove another important theorem, very important theorem. Theorem says that set of all real numbers is a uncountable set. That is, set of all real numbers is not countable. This is very important theorem and the last theorem of this module. Okay, now we are going to prove that set of all real numbers is an uncountable set. Okay, we know that closed 0 1 is a subset of R. Closed 0 1 is a subset of R. Closed 0 1 is a subset of R. Now I am going to prove that closed 0 1 itself is an uncountable set. Closed 0 1 itself is an uncountable set. That is, smaller set closed 0 1 is uncountable. Then from this we can say that the bigger set are also an uncountable set. I am going to prove set of all real numbers is uncountable by proving its subset closed 0 1 is an uncountable set. Okay, now I am going to prove that my aim is closed 0 1 is an uncountable. To find my aim is closed 0 1 is an uncountable set. My aim is to prove closed 0 1 is an uncountable set. For a contradiction, assume that closed 0 1 is a countable set. For a contradiction, assume that closed 0 1 is a countable set. So I assumed that closed 0 1 is a countable set. So we can be written as closed 0 1 as is in this form. That is, closed 0 1 is like x1, set x1, x2, x3, x4, etc. Since closed 0 1, we assumed that closed 0 1 is a countable set. So we can write closed 0 1 equal to set x1, x2, x3, etc. Now I am constructing some intervals like this. That is, let I1 is a closed sub-interval of I. I is closed 0. I is closed 0, 1. Now I am going to construct a new closed sub-interval of I, that is I1 subset of I. I am going to construct a closed interval I1, which is a subset of closed 0, 1, that is, which is a subset of I, which has the property that I1 subset of I is closed 0, 1, and I constructed the closed interval I1, which is a subset of closed 0, 1, and one more property is that the element x1 not belongs to I1. X1 not belongs to I1. That is, I1 has two property. First property is that I am going to construct a new interval I1, which has two properties. First property is that I1 is a subset of I. I1 is a subset of I. I is closed interval 0, 1. And the second property is that the element x1, this element x1 not belongs to I1. X1 is not contained in I1. That is I1. Now again I am going to construct a new interval I2, which has two properties. The property is that I2 is contained in I1. We defined I1 just before. The new interval I2 is, I am going to construct I2, which is a subset of I1. I1 is just defined above. And the second property is that x2, the member x2, this member x2 not belongs to I2. X2 not belongs to I2. That is, I2 is a subset of I1 and the element x not belongs to I2. Continue this process. If we continue this process, we will get I3. Which must be a subset of I2, and x3 not belongs to I3. Continue this process, we will get the intervals I1, I2, I3, etc. I1 is the bigger interval, that is I1 superset of I2 superset of I3 superset of, etc. That is In plus 1 is a subset of In, and the element xn not belongs to In. We know that x1 not belongs to I1, x2 not belongs to I2. Similarly, the element xn not belongs to In for every n. Okay, we got nested sequence of intervals I1, I2, etc. I1 is the bigger interval, superset of I2, superset of I3, etc. Okay. Then by the nested interval property, we before we proved that by nested interval property there is an element z. Z belongs to In for every n. Z belongs to In for every n. That is, Z belongs to In for every n, and every In means Z belongs to I1, Z belongs to I2. By nested interval property, we can find an element Z which belongs to In for every n belongs to n. That is, Z is a member of I1, I2, I3, etc. Every In we have Z is contained in that in. Okay, so z belongs to I1. Since z belongs to in for every n, we have z belongs to I1. Since z belongs to I1, we know that x1 is a node belongs to, we know that x1 is node belongs to I1. Therefore, z not equal to x1. Z not equal to x1. Since x1 is a node member of I1 and zeta belongs to I1, so zeta not equal to x1. Similarly, we know that z belongs to I2, which means that z not equal to x2. Since x2 not belongs to I2 z zeta x2 not belongs to I2. Since x2 not belongs to I2, we have z not equal to x2, etc. That means z not belongs to the set x1, x2, x3, etc. Which means that we assume that this set is equal to closed interval 0, 1, which means that zeta not belongs to close to 0, which is a contradiction. Since zeta belongs, which is a contradiction, since we have zeta belongs to in for every n, which means that zeta belongs to close to 0, 1. But we got that zeta not belongs to close to 0, which is a contradiction. Therefore, our assumption is wrong. Our assumption was closer to 0, 1 is a countable set, which is wrong. That means closer to 0, 1 is uncountable set. That means R is not countable.